Welcome back again to our video lecture in ENSC107. And in these videos, we'll be doing some more problems regarding the forces on submerged bodies. Now, for our problem number 3, we have this problem, and it states that a circular storage tank contains vinegar, and the density of the vinegar is given, and that's 1040 kilograms per meter cube. As shown in the figure, a viewing glass is installed at the bottom portion, and the problem says we are to determine the resultant force and then the location of that resultant force on the viewing glass. Okay, so in the figure we have this. This is the circular storage tank, and since it is not fully filled, so we have these dimensions, 0.25 from the top, and then we have from the free surface we have a 4-meter depth to the centroid of the viewing glass. Now this type of problem, I guess, is not this is just an open tank, so that means that the free surface is exposed to the atmospheric pressure. Okay, so in that way, if that's exposed to the atmospheric pressure, then we can just work on the gauge pressure. Okay, so again, when we say we'll be working on the gauge pressure, that means that the free surface is a zero pressure with respect to the atmospheric pressure. Okay, so let's now draw. Okay, let's now draw the pressure profile. Okay, so drawing the pressure profile. Okay, so this is our tank, then this is the bottom of the tank, and we have our viewing glass right here, and the distance from the free surface, this distance to the centroid of the viewing glass, we have 4 meters. Okay, and therefore our pressure profile would look something like this. However, since we are only considering the forces on the viewing glass, then the portion will only be just this one shown in the drawing. Okay, so this portion only. Okay, so now we can solve for the resultant force. Solving for the FR, so that's FR is just simply this one, the unit weight times the average height, or that's the height to the centroid of the surface concerned, okay, times the area, and then the area refers to the area of the viewing glass. Okay, so we have the mass density of 1040 times 9.81, that becomes Newton per meter cube, times the height of 4 meters, then the area of pi d squared, which is 0.5 squared all over 4. Okay, so right now I'm not using I'm not writing the units, but just keep it noted that these are in kg per meter cube times the gravitational acceleration, and that becomes Newton per meter cube. This one is in meter, and this one would be meters squared, so the resulting units would be Newton. Okay, so let's solve this. 1040 times 9.81 times 4 times 0.5 squared divided by 4, that's 8,012.9 what's this, Newton. Okay, or we can just roughly say 8 kilonewtons. Okay, so the next step is to solve for the location. And we have this equation y Cp is equal to simply the y bar plus the I, then the area times the y bar. Okay, so the centroid along the y direction. Now it's just the same as the h because it is vertically, the position is vertical, so that's why HL H bar is just equal to the y bar. Okay, so this one is 4 plus the this one, the area moment of inertia can be taken from the tables, and we have our equation pi d squared all over 64. Okay, so times the y bar times the area, which is pi d squared all over 4. Okay, so this one, this numerator cancels out, then this also, so we just have 4 plus 1 over 64. That's 4.002 meters. Okay, so that's just 0.02 meters lower than the center. Okay, so now we'll move on to another method of solving these hydrostatic forces, and that's the method of the pressure prism. Okay, so we'll write it here, geometric method. Also, it's known as the pressure prism. Right, now let's draw again a surface, let's say a vertical surface, and that a portion of this surface is submerged in a liquid. And if we draw the pressure profile, we get this one. Right, so it's basically a force distribution acting on this area. Okay, so when we say prism, this actually refer to this solid volume of the pressure profile. Okay, so pressure prism, or we can just say it's a solid. Now the question is, what is the volume of this solid or this prism? Okay, so the volume here is basically, it's just the area, right? So we have this area, we have the area right here, right? So that's the area times the length here. Okay, so if we draw it here, this line right here is the this one is the H. Okay, so this one is the height or the depth of the fluid, and then this one would correspond to the pressure. And if we label this as our z-axis, right? So this is our z-axis, and this one is the h. Then this one would be our pressure. So it's like we're having this universal coordinate system as this one is the pressure, then this one is the h, and then this one is the z. Or you can just think about it as x, y, and z. Okay, so what is the volume? The volume is just simply the pressure. Okay, so that's the pressure. This one, the area times the orthogonal length. So this is the pressure times the height, P times H. Okay, so since this is a triangle, then that's gonna be P times H over 2. Okay, times the orthogonal length, which is Z. Okay, so now what is H? What is H times Z? This one. What is H times Z? Okay. H times Z, that's actually the area, right? So let's write this area, and we get P times A all over 2. And what is P? P is simply the hydrostatic equation, the unit weight times the height, right, times the area all over 2. Okay, and we now know that it is now clear to us that this volume is actually the total force, the amount of force that's acting on this area, okay, given a pressure. Okay, so recall from our previous equations the analytical method that the force, the resultant force, is just the area, the pressure times the area, except that what we used earlier is this notation, times A. Now this one is the something like the mean depth. Okay, and if that's the mean depth, this would be our centroid. If this is our centroid, that refers to this one. Okay, so that's why this is different. This h bar is different from the h. This one refers to the total depth, whereas this h bar refers to the depth from the free surface to the centroid. That's the vertical depth. Okay, which is just simply equal to h over 2. Okay, so they are actually the same. Okay, so now let's try to build our skills on these volumes. Okay, so now let's try to consider this triangular prism. Okay, and it is also possible to have a rectangular prism or a combination of both. Okay, so for this one, triangular, and this one is rectangular, and as I have also said that it is possible to have a combination of the two. Okay, so this is what we call as the trapezoidal. Okay, so for the triangular, we have FR. Then recall that, as I've said, that this FR is simply the volume of the solid. Okay, so this one is, let's say this is our P, and then this is our H, and this will be our Z-axis. Okay, so for these solids, we have the pressure, which is just equal to the unit weight times the height, okay, divided by 2, okay, times the h, this side, times the length. Okay, so we can simplify also that the FR is just the unit weight times h squared all over 2 times z. Now for the rectangular, if this is our pressure, this is our height, this is our orthogonal length, then our FR is just simply h squared times, unit weight times h squared times the z. And for this one, we can just break this down into triangular or rectangular. Okay, so let's now work on one problem regarding the use of this method. Okay, so for this problem, the problem number 4, the problem states that find the magnitude and location of the resultant force acting on the side wall of a 1 meter square tank of 2 meter depth. Half of the depth is filled with a liquid of a density of 1,500 kg per meter cube, while each other half is filled with water. Okay, by the way, this problem is taken from this textbook by Cruz et al. Introduction to Hydraulics. Okay, so that's example number 4.5. Okay, so it says we have a square tank. We have a square tank. The cross section is a square, and the depth is 2 meters. So it says half of the tank is filled with, let's say, fluid A, and then another one is filled with water. So Sg is equal to 1.0. This one is Sg is equal to 1.5. So if it's half, then the depth would just be 1 meter and 1 meter. Now, since we have two fluids here, two types of fluids or two kinds of fluids, then we would have a different slope for the hydrostatic equations, because as you can see in our equation that delta P is equal to negative the unit weight times the delta H. Now if we rewrite this hydrostatic equation, what we get is this one. And since this is along the x and along the y, but in terms of function, this is the dependent variable, and then this is the independent variable, and we see that this one is the slope. Okay, slope of the line. Okay, so for the solution, okay, so the first thing that we need to do is to visualize the pressure profile. Okay, so since this is square, then we can just choose whichever side. Okay, and now we'll write our okay, so we have Sg is equal to 1.0, and this one is Sg is equal to 1.5. So the pressure profile with this probably would look something like this, and this one would have a pressure profile something like this. Okay, so this one is 1 meter, and then this one would be 1 meter. Now let's write this is figure 1. Okay, and then the next thing to do is to probably draw this this profile in a three-dimensional view. Then what we can get is something like this. Okay, so this is our pressure profile. Now we can, since we have a triangular profile on top and we have a trapezoidal profile at the bottom, then we can just simplify this into a rectangle plus the triangular portion. Okay, so now let's label this as our profile number 1 or prism number 1. This is prism number 2, and then this one is prism number 3. Now if we label the dimensions, we have 1 meter, 1 meter, and this one would also be 1 meter. Now let's label this as figure number 2. Okay, so now solving for the resultant, or for the forces in each prism. Okay, so FR1, this is a triangular, so that's just simply the unit weight or I guess it's more careful if we use the pressure axis. Okay, so this is our pressure line. I mean, we are referring now to the x-axis or along the x-axis. Now if this is 0, then the pressure at this point, right, the pressure at this point would be let's say P sub B, and then the pressure at this point would be, let's say, P sub C. So I guess let's solve for PB and PC. Okay, so PB is just simply our PA, or the initial. Okay, so from this portion, this is our PB, this is our PA, which is a 0. So PA plus this one times the unit weight and the delta H. Okay, so since this is 0, then this one is just 9,810, and this would be 1.5 times 14,715 Newton per meter cube. This one will be Newton per meter cube. Okay, so PB is just equal to 9,810 Newton per meter cube times 1 meter. So PB is just 9,810 Newton per meter cube. Okay, and then PC would just simply be PB plus the unit weight, right? But this time the unit weight, because we are referring to this region or this portion, and that's going to be the unit weight of this fluid. So that's going to be 9,810 plus the unit weight, which is 1.5 times 9,810 times 1. So this one is 24,525 pascals. So, sorry, this one should be pascals also. Okay, and note that this pressure at C refers to pressure from point 0 to point C. And now what we need is the pressure from PC to PB, which is just the PC minus PB is just equal to 4,715 pascals. Okay, so we need these values of PC because we are solving for the volumes. Right, so now let's solve for the forces. Right, solve for the forces. So for prism number 1, F1 is, okay, so this is our F1, our pressure right here. Let me draw it here again. So our pressure number 1, this is PB, and that's 9,810. And this one is 1 meter, and this one is 1 meter. Now for the pressure at prism number 2, so for prism number 2, this one is 14,750, and this one is 1 meter, this one is 1 meter as well. And for the prism number 3, we have a rectangular prism, and this is 9,810, this is 1 meter, and this one is also 1 meter. Okay, so for the prism number 1, we have 9,810 times 1 meter, right? The area of the triangle divided by 2 times the this length. Okay, so we have 4,905. That's Newton. And then for the force on prism number 2, we have 14,715, right, times the height, which is 1 meter, all over 2 times the orthogonal length, which is 1 meter. And then for prism number 3, we have a rectangular, which is simply 9,810 times 1 times 1, that's going to be 9,810 Newton. And this one is 7,331 Newton. Okay, so now we're done with the forces. And to solve for the location of that force, then we can okay, let's write here solving for CP. Okay, so now let us draw again the pressure profile, and we have this. It is our 1, this is our 2, and then this is our 3. Okay, so now let's locate the centroid of this area. Now for the prism number 1, the centroid is 2/3 from this. Okay, so that's 2/3. Okay, so 2/3 times 1, so it's just 2/3. And this one, the centroid of 2 is somewhere right here. Again, 2/3 from this point. And this one, the third prism, is we have the centroid at the midpoint. Okay, so for this, we have 1.5 meters, because this is 1 meter, and the distance from this point to the centroid is 0.5 plus 1 meter, so that's why 1.5 meters. And this one would be 5/3 meters, right? And if we write here the location, the magnitude of the forces, so this one is F1, which is 4,905. This one is F3, which is 9,810, and this one is F2, 7,357.5. Okay, so if we do the moments, we have FT, the Ft is, okay, let's sum up the forces first, which is just F1 plus F2 plus F3. So if you sum the value, what you get is 22,072.5 newtons. And therefore, if we multiply this Ft times the y, or the distance to the center of pressure, it's just simply the sum of the individual forces in their corresponding location. Okay, so let's just write y1 plus f2 times y2 plus f3 times y3. Okay, so we have the value of all these terms plus the total force, and now we can solve for ycp. So ycp is just simply, if you substitute all the values, what you get is 1.37 meters. Okay, so since this is our reference, then the value of the resultant force would be 1.37 from the reference point. Okay, so just a review of what we did in this problem number 4. We used the geometric method, or the pressure prism method, and we first draw the pressure profile, and what we did is to solve for the pressures at the special points. Okay, so like this, because that's the point where the slope changes. Okay, so we first solve that using the hydrostatic equation, and it's simply because the pressure is the x-axis. Okay, so the next step that we solve is, since we already obtained the values of the pressures on this axis or on this side, then we can find the volume, and the volume is simply that volume corresponds to the force, or the hydrostatic force. And once we have that, then we can solve for the total force. And in order to solve for the now to solve for the center of pressure, it's just simply the force times the moment arm. Then this one also, the force times the moment arm, or the idea is that the total force times its moment arm is just simply the sum of the individual forces times its moment arm, and we have a value of 1.37. Right, so in the next video we will be doing another problems regarding these methods. Right, so see you in the next videos.